All right, guys, so hopefully you are watching this having already read sections 2.1 and 2.2 that I put up on Schoology. And this video just acts as a summary and alternative explanation of what you've read in the book. So I'm going to jump straight into motion diagrams. I actually took this photo from the book, from the last page of this section, and asked a question to draw a motion diagram. So hopefully you've understood motion diagrams are diagrams that represent motion, but in a 2D format where no motion is taking place. And normally we have something like this image that's literally shown right here, where this car is moving through it. Now, you don't want to have to draw a car every single time you want to create a motion diagram of a car coming to a stop. That's a lot of work, that's a lot of effort. So what we use instead are called particle diagrams. And what that basically means is that you just replace the image or the object with a particle, a literal dot that represents everything about the image. So I'm going to just finish writing diagram really quick. And we'll talk about this here. Now, I am not an artist at all. I do not know how to draw a car. And again, that'd be a huge waste of time in general. So when we're talking about particle diagram, what we want to do is we replace the image with a single particle with a dot. And now you could put this dot at any point of this image. So I'm going to see if I can zoom in on this car right here. If you put the particle in place of maybe the front tire, that's acceptable. I mean, you're still going to show a motion diagram. But the ideal is that your particle replaces the center of gravity of these objects. Basically, where is the most mass happening in these pictures? Now, that might not make sense, but basically, you just don't want to choose maybe the very back end of the car when you're choosing a particle diagram. You want it to correspond with really, again, the center of gravity, the middle of the car. So for this one, I would put a dot right here. For the second one, maybe right here. Now, these aren't perfect. That's fine. I'm just trying to sketch from the middle of the car downward. And now your hope is that you see that these points get a little bit closer every time, or rather, right here, they're a little bit farther apart. So it shows that the car was moving a lot faster, and then it starts coming to a stop, and suddenly you see that our distances between get a little bit more even, right? That's what a particle diagram is. It shows motion over time, but just with simple dots instead. And then you want to include, your own origin and everything else. So you could put like a 0 here for the stop sign or whatever it might be. But that's pretty much the basics of it. So I cleared up my picture a little bit. I kind of tried to put together a start and a stop. I just realized now that I put stop on both of them. But let's assume that on the right-hand side that said start, on the left-hand side it correctly says stop. That's what kind of a coordinate system is. So you're basically defining what's your origin, where's your starting point, what is 0, and what is positive and negative. So I've drawn this really vague origin system. It's not perfect. The lines definitely aren't lined up very well, but it gives kind of an idea. So in the middle, let's just say that's Reardon, right? And so Reardon, let me put this in there. Let's call this Archbishop Reardon High School. This is our origin. So our origin, or our starting point, is going to be the value of 0. And now commonly when you have a coordinate system like this, the line to the right is your positive direction, and your line going to the left would be your negative direction. That's just normal convention. So I'm going to put some numbers on here. I'm going to change my word to the right word, and we will go from that. Okay, so I made a few changes, and again, this is our coordinate system. So I purposely wrote negative direction and positive direction in here. And now it's up to us to kind of figure out, what does that mean? So if we had someone travel, I'm going to use a little bit bigger marker to kind of show this here, travel from 5 miles in the negative direction to Reardon, do we say they traveled -5 miles? Or do we say they walked 5 miles from the left? And that's kind of what our coordinate system really kind of helps us figure out here is directions. So a negative direction based on convention is actually left. So let me add that in here. Let me change colors really quick. So we have it all in here. This really means left. It gives us, this coordinate system gives us an understanding of where their relative positions are for motion diagrams. So we know that this little blue dot up here came from the left, moved to the right in order to get to school, which makes our positive direction the right direction, right? Not like it's the correct direction, but they are physically moving to the right. And that's really what our coordinate system is supposed to help us figure out. It's giving another aspect to that motion. It's not just, oh, they moved in a straight line, but now we know they moved in a straight line left or right, east or west. So now let's give some terminology to this arrow here. This arrow is what we call a vector. So a vector shows direction, which is negated by the actual arrow, and also magnitude. So the size of the arrow lets us know how big it is. So vector shows size, which is magnitude, and I'm going to write that in a second, and direction. So let's get that in there. Now, it's very easy to see because of our coordinate system that this particular blue dot kid walked a pretty good distance, right? I know I haven't put units on it, so that could be 5 feet or 5 miles, but let's say it's 5 miles. He walked a significant different distance to get to Reardon. Now, what if we had a kid, oops, let's take that out, right here. So this is their vector, something that shows, again, direction. Ooh, that was terrible. Okay, bear with me. It shows a direction again, a really terrible arrow pointing towards Archbishop Reardon, and it also has a size. Now you can physically see that that size is smaller, and we want to really focus that on vectors. If someone in your motion diagram or something moves 10 miles, that should be a significantly longer arrow or vector than someone who moved half a mile, right? It is all about that size and direction. So a vector is always represented by an arrow. So an arrow can be pointing up, down, left, or right, totally whichever way the direction is. And opposite of vector, we have scalar quantities, just to put these vocab words up again. So a scalar quantity is just a number. So instead of me drawing this arrow on the motion diagram above, right, to show that the kid had walked 5 miles, a scalar quantity just looks like, oh, let me get this up. An example of that would just be a number, right? Literally writing out the word 5 miles. We don't give a direction in this, so it's just a scalar quantity. All right, so there's only one last thing I want to talk about in this video, and that's displacement. So I erased my vector quantities on my coordinate system, and I am changing my color so we can talk about displacement. Now, I'm going to write this word down, and I'm going to write the equation down. Not exactly its definition, and the equation might be confusing, but that's all right because we'll have a chance to talk about it. So the equation looks like this. And if you didn't fully understand it from the book, or you didn't read the book and you're just seeing it right now and not understanding it, that's all right. We're going to talk through it. Displacement is very easily mistaken for how much distance have you moved in a day. But that's not what this is. Displacement really is how far you have moved from your origin in a day. So I'm going to write that down. Now, when I say how far you move from your origin in a day, I also mean how far you've moved from your origin in any given amount of time. So it just depends on what your parameters are. I am going to start a little diagram. Now, let's say that someone started at Archbishop Reardon High School. They're leaving for the day, and let's say they have to walk home. So they walk 3 miles out, and then realize, oh no, I have left my phone at school. So they immediately turn around, because you can't leave your phone, and they start backtracking to the school. Now, once they hit 1 mile, their friend actually comes out of school and says, hey, I saw you forgot your phone. I've got it for you. So that person, now happily with their phone, picks it up, turns around, and walks all the way home. So this person has done a lot of walking. In total, they've walked, 3 miles to start with. So I'm gonna just highlight these out so you can see what I'm talking about. So they started with right here, they walked 3 miles out, and then they turned around and walked another 2 miles back in. So they've already walked 5 miles, and then they walk another 3. So they've walked 8 miles total right now. But that's not really the displacement we want to talk about. So when we say displacement, let's talk about this equation. Now, this triangle here, in math, that triangle stands for change in, or the difference, right? Change in or difference, that's what it is. Here, this little subscript of F stands for final, so it's actually saying, hey, take your final position and subtract from that your initial position. So we just want to know what their displacement was. How far away from school are they now? So setting up this problem, their final position, if we look, back up at this graph, is right here at 4 miles. And their initial was at Archbishop Burden High School, which we said was the origin of 0. So their final was 4 miles. And their initial position was 0 miles in. So their displacement overall is just 4 miles. Now, bear with me for one last change of this picture, this example. Let's say that for some reason the kid forgot a piece of homework at home, and his parents said, nope, you have to go back right now. Go get your homework. So he, starting right here from home, walks all the way back to Archbishop Burden High School. Oops, let me change that. So he goes all the way back. What's his displacement now? Well, let's write it down. Maybe if I can get this to work. Here we go. So now for this very last one, his final position is the origin. It's at 0. So we're putting 0 miles in for his final position, and we're subtracting his initial position. But let's say we're subtracting his initial position at the beginning of the day. So where did this all start from? It all started initially from Reardon High School. So again, at the origin of 0 miles. So his displacement from the minute he left school till he went back to get his homework was 0 miles. That's the total displacement for him. And that seems a little weird because he's walked, a ton of miles. He's walked so many miles now, right? But in terms of displacement, he's only displaced himself 0 miles, excuse me. So he really doesn't look like he's gone far in terms of displacement. So we've gone over a little bit of a particle diagram, a bit of what coordinate system means, what vector and scalar magnitudes are, and displacement. So this is hopefully just a review. You've already seen it in your notes and in your readings, but if you have any questions, please make sure to ask them next class.